So all I need to do is go back to me. There I am. Oh, as always, my glasses are reflecting my lamps. Which one is that anyway? Is that this one? No. Is it this one down here? Yeah, see, if I move my hand around, I can see it's that lamp. And if I could diffuse that a little bit, maybe like that? That's better. But no, it's not really doing its job of illuminating me, which is what a lamp is for. You know, lighting is like the hardest thing to do in a video. I'm always amazed. And after now doing a few documentaries and doing stuff like this and all that, whenever I see a show that's well lit, I always like, oh, look at how they lit that. Isn't that awesome? And my wife is just, stop telling me about how well it's lit. And it's like, it's so cool. Anyway, it's funny how you notice things like that when you start doing it. Okay. Hey, folks. Welcome to Q&BA, my live video chat on air with Google Hangouts for February 12th, 2012. This is where I basically am available to you guys just to answer questions. I know a lot of stuff because I've been alive a long time and I do a lot of reading and I have a lot of opinions and I'm interested in a lot of stuff, and I know you guys are too. You like space and astronomy, or else you wouldn't be listening to me. Duh. So it's a chance for you guys to ask me questions and a chance for me to try to figure out if I know enough to actually answer them correctly. No guarantees. So let's see. We're just a couple of minutes into this. I actually want to start this week by just talking about a couple of things that caught my interest this week. One thing I want to tell you right away. Oh, and I can't even show it. What happened to my picture? Here? There we go. It's funny, I have to screen share stuff. Here we go. There we go. I've got a couple of things I'm going to do a little bit differently this week because I'm just playing with ideas. One of which is that I've made some notes. And let's see here. I'll put these in the actual Google Plus feed where I'm doing this. And sorry, this is live. So there's going to be a little bit of me looking around and doing stuff and all that. First, I'm going to put up a link to there we go. Tonight, there we go. Okay, so tonight, between 10 and 12 a.m. Universal Time, which is Greenwich Mean Time, GMT. So that's actually, for people in the United States, it's going to be in the middle of the night. For me, it's in 3 in the morning. If you're in London, it's actually between 10 and 12 in the morning. The European Space Agency is going to launch a new rocket called the Vega. It is a small rocket, actually. It's not a very big one. It's orbital. It will actually launch payloads into orbit, but it's not like the Space Shuttle or the Ariane or a Titan or an Atlas, one of these big rockets that can launch a huge payload. This is specifically designed to launch smaller satellites, smaller payloads into orbit. The main payload of this rocket, actually, is a science experiment that only weighs, it has a mass of, I think, 390 kilograms. So 390 kilograms is like a third of a ton, which is relatively small for a rocket payload. You know, Hubble weighs many tons. Hubble's a big payload. Maybe that's unfair. But there is a market for these smaller things. This is actually launching 9 little satellites into orbit. It's the maiden flight of this. This rocket has never been sent to orbit before. It is the qualification flight. So in other words, they're going to launch this thing up, and they're going to test everything from all of their ground systems, their telemetry, everything, from countdown to getting this thing on orbit. So that's really cool. This is your first, this is a chance to see your first flight of a totally new rocket. The link I just put up in the room goes to my blog where I have links to more information about this launch, where you can watch it live, links to some of the satellites that they're going to be putting up and all that information. That's pretty neat. I'd love to watch this live. 3 in the morning my time here in Mountain Time, so not going to do it. The launch window is 2 hours long, from 10 to 12 in the morning, UTC again. So you can go online, look up wherever your time zone is and how far off you are from Universal Time, and you can check that out. Now, for everybody, not just people who happen to be up at the right time, for basically everybody, if you have clear skies tonight after sunset, look to the look to the west, right? So you watch the sun go down, look in that direction. Once it gets dark, and even before it's dark, Venus will be up in the sky. It's the brightest object that'll be up in the sky. The moon won't be up, I don't think, and Jupiter is going to be up above it. They're the two brightest star-like objects in the sky. They're unmissable if it's clear out. If you have clear skies, once the sky is dark, not twilight, but actually dark enough, take a pair of binoculars and look at Venus. Put it near the top of your binoculars. This is for the northern hemisphere. For the southern hemisphere, yegads, I'd have to think about this. I still think that's correct. You'd be upside down. Venus would still be setting. Yeah, wow, that's actually not so easy. But you know what? Tell you what, in the show notes, in the Google Plus room, here is a map of the sky for you to go to, and you can use this. You put in your coordinates. This is at Fermilab actually. It's called Your Sky. If you look that up on the web, you can find it. Here's where you can do this. Post comment. There you go. If you go there, you can put in your coordinates. Sorry, I know I'm bopping around a little bit. You can put in your coordinates, and you can have it show you where you're looking in the sky. And I will screen share this. I actually put in my coordinates of Boulder, Colorado, which is roughly 40 degrees north and 105 degrees west. I told it to look at an azimuth of 264 degrees. Azimuth means horizon direction. So 0 is north, 90 is east, 180 is south, and due west is 270. So this is just a little bit south of west. I also told it to give me a 15-degree field of view. You can see that here. There's the viewpoint here, azimuth 264, field of view 15 degrees, and a time for me of 3 in the morning UTC. I subtract 7 hours for that, so that's roughly 8 o'clock at night for me. So this is after sunset. The sky is dark. Here is Venus up in the sky, a few degrees above the horizon. Just below it, if you look at Venus with binoculars and you put it near the top of your field of view, you'll see a star here and another star here. I'm hoping you can see my mouse. That is Uranus. Now, I actually went out and looked for Uranus and Venus the other night, and it was actually quite easy. Venus is moving around the sun, and so its position is changing every night. This is for tonight in about 9 hours from now. You can put in your own latitude and longitude, put in put in an azimuth of 270, whatever, fiddle with the field of view, I don't care, and that will show you where Venus and Uranus are in relationship to each other tonight. Venus and Uranus are pulling apart, but right now they're just a few degrees apart right now, so they're easily visible together in binoculars. I actually put up my telescope. I put this to my telescope the other day. Ooh, my video's frozen. Hope you all can hear me. Let me go quickly check the chat room. Make sure you all can see this. Let me scroll down. Okay, it looks like you all are not complaining. Is my video frozen? I can see my audio is working. There we go. Okay, sorry about that. So I actually went out with my binoculars, which you can see behind me right here. They're actually pretty nice binoculars. They're big, but you don't need huge binoculars. Uranus is at about magnitude 6. Maybe a little bit fainter than that, but that means that it's actually, if you have even relatively dark skies with a pair of even small binoculars, like these guys right here, this is just your regular old field binoculars there, you should be able to see it. It'll be a faint blue star. I actually had it, I put it up in a planetarium program I have on my iPad, and when I look in here, I see 7 or 8 stars that look like they're roughly the same brightness as Uranus. If you have dark skies, Uranus will be blue. It's actually bluish-green, and so that will distinguish it from the other stars in the sky, which typically look white or somewhat yellowish. And when I looked at it through my binoculars, it was pretty obvious the other night. When I looked at it through my telescope, I have an 8-inch telescope, it was a tiny, perfect disk. I could just see that it was a disk under low power, and it was just a beautiful, it's like an aquamarine or a teal. It was lovely. Then I went off and looked at Jupiter, actually, and this is funny, I took my iPhone, just have an iPhone, held it up to the eyepiece, which was actually pretty hard to do, just handheld it, I took a picture of Jupiter through my telescope and saw this. And you can see here's let's see, I have to do it, I believe, this way. Here we go. So here's Jupiter overexposed. I couldn't help it. These are two moons of Jupiter here and a third one over here. I think this is Io and Europa. I may have those backwards. And Ganymede over here. These are just three moons of Jupiter. It just goes to show you that even through a small telescope, and 8-inch, it's a pretty nice telescope. It's a Celestron 8-inch Schmidt-Cassegrain, for those of you asking. It's pretty nice. But you don't need a huge telescope to be able to see Jupiter as a disk. And to the eye, I could see the bands, the stripes going across Jupiter very easily in a little bit of detail. And I wasn't even really trying. So if you can go out and you have a friend with a telescope or you have a telescope, it's pretty awesome. These are really good nights. You've got Venus, Uranus, Jupiter's up. I also looked at the Orion Nebula, a couple of other things, and it was like, in centigrade, it was like 10 below. It was really flippin' cold the other night. But it was easy to do and it was a lot of fun. If you want to find this stuff, go to that Formulab link and you can find all that stuff. There are other wonderful planetarium software websites up there, stuff you can download to your computer. I see Matt Tinney's already linked to Stellarium. That's a really good one. I've used that one for many, many, many years, and it just gets better all the time. There's one other thing I want to show you, because this is funny. I got this in the mail the other day. It's an advertisement for Shutterbug, which is a photography magazine. I don't know if you can see this. Let me see. So see what it says there? See what their logo is? Shoot like a what? Shoot like a poo? I don't want to shoot like a poo. And I have friends who are typography people, like Donna, Misinformation. If you're familiar with George Hrab's podcast, Donna's his producer, and she does a lot of stuff. She's a typographer, and I tease her about liking Comic Sans all the time. I like Comic Sans. She hates it, because all typographers hate it. But this is where typography is important, folks. You don't want to shoot like a poo. Shutterbug's actually a great magazine. A magazine, or is it online? You know what? I've gone there. Yeah, it's a magazine. But I just think that's really funny. Just choose wisely. And that's it. Those are all of my little news items. So you can follow me on Twitter at badastronomer. I'll be taking questions from there. Follow me on Google+. My website is badastronomy.com. Also, just a little announcement, this is brought to you by Science Getaways, Vacation with Your Brain. My wife and I have started a company where we're going to add science to normal vacations. So if you go to sciencegetaways.com, you'll see our first one is going to be in Colorado in September, where we're going to a dude ranch, and I will be doing star parties and talks and showing you the skies at night, and hopefully during the day we'll look at the sun. We have a geologist and a biologist. We'll be taking nature hikes, and it's a fantastic dude ranch. It's lovely there. The food is amazing. We got a really good deal where it's actually less expensive for you to book it through us for Science Getaways than it would be to do the dude ranch normally. So I hope you all will join that and do that. It's a lot of fun. Okay, so. All right, so I'm going to start taking questions, and I will just set things up right now. Okay, no questions on Twitter. It's funny, I don't get too many questions on Twitter here, which is interesting. There's a difference between Twitter and Google+. I'm still trying to figure out. I'll tweet things, and it's like throwing something off a cliff. And then I'll put the same thing on Google+, and it goes viral. So, I posted that picture of Jupiter, that crappy picture I just took, put it on Twitter, and a bunch of people said, that's really neat. I put it on Google+, and it actually hit the what's hot. It's like, really? A blurred, out of focus, overexposed picture of Jupiter I took myself. So clearly, there may be a connection thing on Google+. People want to connect with people and things they've done themselves versus, posting a gorgeous Hubble picture of Jupiter, which is, something you could make as your desktop. Yeah, I'm still trying to figure that out. It's very interesting. All right, so, people were saying my video was frozen. Sorry about that. That's going to happen sometimes. This is live. I'm doing this in my house. This is my office. This is where I work. And, sometimes the internet gets a little plugged. So, what do you do? All right, so I saw a question here earlier. Okay, now, I am an astronomer, okay? I'm not a research astronomer anymore. I haven't done any of my own research in many years, but I did work on Hubble. I worked on various things, and I try to keep up with stuff. Having said that, I don't always know exactly what's going on. There's a lot of cutting-edge stuff, so I may not be familiar with that. Like if somebody says, what causes this? I may not know. Hopefully, though, I can direct you to places where you can find stuff. And so this first question here from Ian, wait a minute, Ian Denniston, I answered one of your questions last week, didn't I? But I'll do it again. Question. Read an article that says the sun's corona is massively hotter than the sun's surface, and we don't know why. Is this true, and do we really not know why? And he has a link to an article actually from cracked.com. I like cracked.com. They put up these lists of like 10 things, 10 reasons why, this. And they're usually very funny, and they're very snarky and tongue-in-cheek. This one is, I saw this one, 6 scientific discoveries that laugh in the face of physics. Okay, first of all, baloney, okay? Nothing laughs in the face of physics. There are things we don't understand yet, okay? There's nothing that is unscientific. There's nothing that is not the proper study of science. And you may be able to phrase a question in a certain way that makes it unassailable to science. But that means you phrase the question poorly, not that science has some weakness. Science is just a method of understanding things, and it's a way of looking at the evidence, investigating the evidence, maybe observing new things, putting them together into a hypothesis, and then testing that hypothesis. And if it's wrong, it's wrong. If it's right, great. Move on to the next thing to try to figure out, to add to it, to figure out how to make it better and more accurate. If you can always phrase a question like, can an unstoppable force and an immovable object both exist? And it, you can have paradoxes and things like that, but who cares? This is a good question because this is just something we may not understand, but clearly it's something that is physically going on. So we just need to figure out what's going on. So the sun, okay, here's my tennis ball sun model of science. The sun is a ball of gas. It's huge. It's 860,000 miles across, 1.4 million kilometers. And it is not a solid. There's no solid part of it. It just gets denser and more compressed in the center. But it doesn't really have a surface. The surface of it just kind of gets lower and lower density and just kind of fuzzes out into the atmosphere of the sun. And it's not like the atmosphere of the Earth because the sun is very hot. And it fuzzes out into the corona. The corona is an extremely tenuous atmosphere of the sun. It's basically a hard vacuum. There's very little stuff there. However, what is there is very, very, very hot. It's much hotter than the surface of the sun. In fact, temperature gets to be a quantity that's difficult to define at extremely low densities. When you have a few million particles per cubic centimeter, temperature becomes a funny thing because these things aren't interacting like they do on the surface of the Earth, where at the air pressure of the Earth, there's 10 to the 19 particles per cubic centimeters. 10 to the 19! Okay, so you're talking trillions of times the density of the sun's corona. When particles can interact, they can share their energies, and then you can measure a temperature. Temperature is sort of that energy of that stuff. When you have one particle, it doesn't really have a temperature. And so it's very complicated, but you can kind of sort of assign a temperature to it. It's not the best way to do things, but you can do that. And you find that the corona of the sun has a temperature of about 1,000,000 degrees. And you might say, how can this thing have a temperature of 1,000,000 degrees when the surface of the sun is only a few thousand degrees? You would expect things to get hot in the center of the sun, get cooler as you move out, and then cooler as you move away from it. But that's not really what happens. And it turns out it's because there's more going on here than simply heating by particles hitting each other, by conduction, literally sharing their temperatures that way, or by convection, where hot stuff rises and cool stuff sinks, or even by radiation, where hot stuff glows, sends out light, which can be absorbed by more matter, and then that heats up. Clearly, that's not what's going on here. There's some other way that energy is being pumped into the corona of the sun, and it turns out it's not, the details of this aren't very well understood, but there are methods of doing that. For one thing, the sun has a very strong magnetic field. And so even though the surface of the sun has a temperature of roughly 6,000 degrees centigrade, there are patches regions of the sun, which are much, much, much hotter, because the magnetic field is basically a way of pumping energy into the gas of the sun. And so when we use things like Solar Dynamics Observatory or the Solar Heliospheric Observatory, which are satellites that look at the sun, they can actually measure the temperatures of the sun. They're looking at wavelengths where the sun is giving off X-rays, and you can only give off X-rays when things have a lot of energy. They have to be very hot, millions of degrees. So in fact, the surface of the sun has these tight little spots that you could say are extremely hot. And some of that energy is getting pumped into the corona. There are other ways of doing it, and these are where, like I was referring to before, my knowledge is a little hazy. I'm not a solar astronomer. But there are these waves that move out from the sun called alpha waves, and it has to do with the way waves move through a plasma and all this crazy stuff that again, I don't understand. And I'm more than happy admitting that. You know, I can't understand everything. Nobody can. If you want to learn more about that, you can look it up. It's Alfvén, ALFVEN waves. If you look up the corona, if you go to NASA websites, SDO, SOHO, these are these observatories, you will find more information about this kind of stuff. You can learn about it. The grand point I'm making here is that I don't know everything. There are people who know more about this than I do. They may not, and even while they're experts, they may not know everything that's going on, because if we knew everything that was going on, we wouldn't need to explore anymore now, would we? So we build these machines, we observe the sun, we're trying to figure this out. And that's where the fun is, right, at these boundaries where we kind of sort of say, well, maybe it's due to this, but what are the details? And so that's what they're learning right now. It's entirely possible that it is well understood why the corona is hot, but there are just some details they're working out. Again, I don't know, but I would say go ahead and look into that, and you'll find that stuff out too. It's a lot of fun, and it's really interesting stuff. I think it's amazing that the sun can have these hot spots in it, but when the cool thing too is that when we look at them, the pictures are gorgeous. And I like it when there are really beautiful images that also have a lot of deep science behind them. I'll be posting something tomorrow about that too on Monday. Totally different topic, but I've got a gorgeous picture to post that has some interesting science behind it. Let's see. Let me check Twitter again. Let's see. I got to pull my glasses up when I look at things close. L. Mateus on Twitter. I think that's an L. God dang it. Boy, the font they use, you can't tell the difference between a little L and a capital I. How ridiculous is that? What a language. See, that typography counts, folks. But he asks, what do you think of a concept of a space habitat? Is it possible to replicate Earth's environment in space? This is a good question. You know what? This is such a good question that I think I can answer pretty well. What I do sometimes, and I have to explain this every week, is if I think I've got a question that I can pull out of the main conversation and it'll stand on its own, I will introduce it separately, and when it's all done, edit it out and put it up on YouTube as its own thing. And I should say that these whole things will go up on YouTube, the whole hour. I haven't done last week because I was going to, and then at the last minute wound up traveling to California to do this thing, which I will be talking about. Let's see, today's the 12th. In a couple of weeks, I'll announce what that is, but right now I can't. But I didn't get a chance to put this up. I'll put that up very soon. So when I do that, I just have to back off a little bit and then say it again. Okay. Hi, welcome to Q&BA, a live video chat where I answer your questions about astronomy and space. Now on Twitter, L. Mateus asked me, what do you think of the concept of a space habitat? Is it possible to replicate Earth's environment in space? The quick answer is yes. Yeah, we sure can. There's nothing physically impossible about doing this. And in fact, in a sense, we've been doing this for 40 or 50 years, actually, ever since we put the first man in space. Basically, a space capsule is a mini Earth environment, right? It's got air in it, there's food that they could eat and water they could drink, and even ways of evacuating their various bodily compartments of things that they want to get rid of. Now, I know that's not what you mean. On the other hand, we've built space stations. The International Space Station is up right now. There was also Skylab and Mir. The Soviet Union back in the day, when there was still a Soviet Union, had put up a bunch of different labs in space. But I think what you mean is something that replicates really what it's like on Earth on a larger scale than something that can just keep 6 or 7 or even a dozen people alive. You're talking about something like out of the movie 2001, where you can actually replicate gravity, right? And it turns out that idea has been around forever too. There are these things called the O'Neill colonies, which are basically gigantic spinning tin cans in space. It's a cylindrical colony. Do I have a cylinder here? I have a paper towel tube. Maybe this will do. You can have a cylinder which rotates like this, and then what happens is you get basically a centrifugal force outward. And so people would live on the inside of this thing, and as it spins around, they would feel a force downward towards their feet. And you can argue about centripetal acceleration and centrifugal force. I'm not going to do that here. The point is, if you're standing on the inside of that thing, you would feel a force outward away from the axis of this thing as it spins. And if you make it very, very large, hundreds of meters wide, it doesn't have to be as long as a paper towel tube. It could be squat like a soup can, for example. But if you make it kilometers long and a kilometer across, you don't have to spin it very rapidly, where that outside force equals the Earth's gravity. And then you can outfit this thing like a little ecosystem. You can put dirt down. You can have rivers flowing. You can have weather in a sense. You could have a light along the radial axis, which becomes your sun, and you could have thousands of people living on these things. It's a pretty interesting idea. It's been around for decades. This idea was popular in the 1970s, these O'Neill colonies. You can have them orbiting the Earth. You can have them orbiting the sun. You can put them out to these points around the Earth's orbit, which are relatively stable points where the Earth's and sun's gravity wind up balancing. I'm skimming over details here, but you can put them there, and they can hopefully be self-sufficient after a while. If you can figure out a way of recycling air, turning our carbon dioxide back into oxygen, you can do that using plants. If you can recycle waste products into food again, and you can stock them with animals and people, you can build a whole society there. And it's not unreasonable to think that this could be self-sustaining forever, because the Earth is basically self-sustaining as long as you don't overpopulate it and pollute it and do all the stuff that we're doing to it. One of these, something like this could last forever. Technically, can we do that? Kind of, sort of. We do have rockets. We do have a lot of understanding of how to do this, but we don't know exactly how to do it right now. The International Space Station is they're components from different countries. They were built here on Earth, launched into space, and then built by astronauts who went out into space and connected these things together. So, and by robotics. So, we have sort of the first few steps into this foray of becoming a permanently, not just space exploring or even spacefaring, but space living species, where we can live sustainably forever in space. We've already dipped our toe into the ocean of the night there. I would love to see this happen. I don't see any reason why not. It's just very, very expensive. But I think it's a worthwhile goal and something that we should be doing. I would love it, if my daughter's kids or even my daughter could take a ride into space and live in space and be able to see out her window the crescent Earth, the Earth underneath as it goes by, or even be farther away than that. What a wonderful future that would be, where we have extended ourselves into space, and that means that no asteroid impact can wipe us out. No virus, no dumb technology mistake will wind up wiping out humanity. And instead of being maybe a footnote in history like the dinosaurs or something like that, our ancestors millions of years from now would remember that, would have records of that. To me, that is possibly the brightest future I can imagine. So great question. Thanks for asking. Okay, now I need to write down what time it is, 11:30, or else I will totally forget when I did that. I wonder how long I was blathering on there. And I hope I answered your question too. All right. Now I shall refresh the Google chat. Oh my gosh, look at all these questions coming up now. Yikes. Here's a question I get a lot, and it's always tough to answer it. But Jonas Kadane, Kidane, it's spelled Kidane, but it might be Kidane. Question, what colleges would you recommend I check out in and around the Texas area that have good physics programs? And then, are there any grants and scholarships, that sort of thing. I am always asked, I want a career in astronomy. What do I do? I'm a physics undergrad. I want to, what do I want to do? It's very, very hard for me to answer this question for a lot of reasons. One of which is that I'm no longer active as a research scientist. I'm a blogger now and a writer, and I'm a Google chatter, I suppose, a hanger-outer. And so, I don't know what's going on in the community. People say, what astronomy jobs are available? I don't know. But I can send you to places like the American Astronomical Society, AAS.org, AAS.org, has a job listings, for example, and there are physics societies that have that as well. I'm also asked, what colleges should I go to? I don't know. That's like asking, what kind of car should I buy? It's like, I don't know. I need more information than that. Are you a very private person? Are you a very extroverted person? Do you study 12 hours a day and that's all you care about? Do you want to go into observational astronomy? Do you want to go into condensed matter physics? Do you like putting stuff together, wiring it yourself? There's a million qualifiers for this, and they're all important. I can't just slough some of this stuff aside. So it's really, really hard for me to say that. And for example, and I get this too. It's like I live in Texas. What do I do? But there are like 100 colleges in Texas you can go to. So I don't know. And if I forget one, I get yelled at, especially from Texans, who tend to have opinions about things, oddly enough, especially when it's inside the Texas border. So all I can do is tell you to do this. On my website, batastronomy.com, go to batastronomy.com/bitesize, BITESIZE, /career.html. If you go there, I have a list of links and some discussions about what to do if you want to get a career in this kind of thing. It's really the best I can do. I don't know what jobs are out there. I don't know what schools are which necessarily, and I don't know what the market's like. They're boom and bust markets right now. I don't know if a lot of people are hiring, or if they're hiring for specific things and not other things. Today is Sunday, February 12th. Tomorrow, the NASA budget. There's going to be a press conference about that, and it's widely rumored. It's pretty clear that there's going to be a $300 million cut from $1.5 to $1.2 billion in planetary exploration in NASA's budget. If that turns out to be true, that means we're basically done exploring Mars. There's no way we're going to be able to afford the next few Mars probes. This is really, really distressing. I know some of you folks are probably going to have questions about that. I don't know anything specific about the NASA budget, so I haven't written about it yet. There are just rumors and things going on. I've got some stuff I'm going to write about. I'm going to wait for the press conference tomorrow to get all my thoughts down. But this is the White House budget, right? The presidential budget, which is where they talk to NASA and say, what do you guys want? Here's what we think we can do. Then they talk to Congress and they hammer it all out. This is the White House budget, which is severely cutting back on NASA. I'm really, really, really upset about this. But I'm not letting that anger be realized until I know exactly what's going to happen. I'm not too, I'm upset about it, but only in sort of a potential way. We'll see what happens tomorrow when it's actually announced. But anyway, the point is, it's always unclear what the budget's going to be in the next year. If you want to be a scientist and you want to be federally funded, your salary is a crapshoot, and it can be very difficult. And so, I don't like giving detailed answers about that. I'd like to give more general things. So if you do that, if you go to that page I mentioned, or look around, that should probably help. Okay, scrolling down. Yeah, I put on my glasses to make me look smarter, but it's hard to read stuff up close. This is a good question. Here we go. I get this one a lot, and it's a little bit complicated, but it's something that confused me when I first heard about it years ago until I actually got into college and did the math and realized, oh, that's how this works. On Google Plus. Let me try this again as a standalone Q&A and see how this works. If it doesn't stand alone, I don't have to worry about editing out. And if it does, hey, free 5-minute video. So yay! All right. Hey, welcome to Q&BA, where I answer your questions about astronomy and space. On the Google Plus chat page, I got a question from Bob Daniel, who asks, can you explain gravity whip, the use of a planet's gravity to accelerate spacecraft? Now, a lot of the times, this idea is called a gravitational slingshot. That's not the best term. It's very graphic. It gives you sort of a mental picture of what's going on, but it's not the really most accurate way of describing it. So what happens? The idea is that you've got a planet, say Earth, and a spacecraft, say, I don't know, this, doesn't matter, a little Earth. But I'll just use this as my model for the spacecraft, the littler thing. And as you approach a planet, you accelerate, because this has gravity. It has very strong gravity. So if you just sort of let this thing fall in, it's going to be moving faster and faster and faster until it gets very close to the planet. And then it's going to start moving away, and it's going to move slower and slower and slower until it escapes, basically. Now, the thing is, Galileo, who first was basically testing how gravity works and all this sort of stuff hundreds of years ago, realized that you can't get more energy out of a system than you put into it. So in other words, if I let go of a rock from, say, 3 meters off the ground, if I let go of a ball and it hits the ground, it can't bounce up higher than I let go of it unless I throw it down. If I just let go, the gravity of the Earth is going to accelerate it to a certain velocity until it hits the ground, and then it's going to bounce up and it's going to decelerate. And at the very best, at 100% efficiency, and I get all the energy out I possibly can, it'll just come back to exactly where I let go of it. It can't be higher. And in real life, it would be lower because there's air resistance, and you lose energy when you compress it and hits the ground and bounces back up. So that's why a ball goes boing, 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 like that. And it's the same thing if you're in space. If I have an object coming in at, say, I'll just make up a number, 20 kilometers per second, sort of a typical interplanetary speed. When it gets near the Earth, it's accelerating. So it's 20 and then 21, 22. It might get up to 25, 26, 27 kilometers per second. But then as it leaves, it slows down. And when it's far away from the Earth, it can't be moving any faster than the speed it originally had. So it'll be moving 20 kilometers a second again. And you might think, but if that's true, then how is it that we take spacecraft and shoot them past Jupiter, we even shoot them past Earth and Mars, a lot of different objects, and they wind up going faster? How does that work? How does a gravitational slingshot work? And the answer is, it's because they're not just moving to the planet, moving away. They're also moving with the planet. This planet isn't just sitting out there. It's actually orbiting the sun. It's going around the sun. And we're going around the sun. So if we shoot a spacecraft to this planet, it's kind of catching up to the planet and then falling in. So there's two different ways of looking at it. There's sort of the planet-centered frame of reference where this thing comes in and leaves. There's also the sun-centered frame of reference where you're catching up to a moving planet moving around. And when you look at it in that frame of reference, the spacecraft, as it's approaching the planet, actually steals some of the orbital energy of a planet. In other words, when we shoot a probe at, say, Jupiter, which is the best one to do because Jupiter has a lot of gravity, as it catches up to Jupiter, this thing is not just falling in and accelerating due to Jupiter's gravity. It's actually being pulled along with Jupiter around Jupiter's orbit. And so it's stealing a little bit of the, basically you can think of it, it's stealing a little bit of the speed of Jupiter. Totally immeasurable. You could shoot 1,000,000 probes at Jupiter and you'd never see the difference in its orbital velocity. But to a spacecraft, which is a tiny, tiny, tiny mass compared to Jupiter's huge mass, it gets a heck of a kick. And you can really shoot out a spacecraft at high speed this way. It's hard to get a probe from here to, say, Saturn, or to Pluto, for example, a New Horizons probe, which is going to pass by Pluto in a few years. However, well, because you need huge rockets to accelerate this thing to high velocity, and that's really hard to do. You need tremendous rockets, and we don't have rockets that big. But if you use a rocket big enough so that you can send that probe to Jupiter, steal a little bit of Jupiter's orbital energy, then you give that to the space probe and it accelerates and moves out much faster. And that's what we've done. We've done that to New Horizons. Cassini did that. In fact, the Mercury Messenger probe did this. It's really hard to drop space probes toward the sun. And so it had to actually pass by the Earth and it passed by Venus. It's hard to do. It's hard to remember what every space probe has done. But the fact is you can do this. And that's what the gravitational slingshot is. It's not that it's stealing. It's not that it's being accelerated by the gravity of the planet alone, it's also stealing the velocity. And you can do this backwards. You can actually shoot a probe in such a direction that it takes energy from the planet and moves faster. You can also shoot a probe so that it basically gives energy to the planet and slows down, or drops it towards the sun. There's a lot of physics that goes on here. A higher energy orbit is actually farther from the sun, but then you move slower. And you think, if I give something more energy, shouldn't it move faster? But it gets a little complicated. When you give something energy, it actually moves out from the sun. So you can steal energy from a planet and move farther out, or you can give energy to the planet and drop it toward the sun, where then it starts moving faster. It's all crazy orbital mechanics. But that's how this stuff works. And that's it. It's a fantastic way of boosting a spacecraft to tremendously high speeds we could never give it with a rocket, because it's just too hard to carry that much fuel. And it basically, because of this trick, it opens up the whole solar system exploration. Planets like Mercury, which are hard to get to because they're closer to the sun, and objects like Pluto, which are hard to get to because they're so freaking far away, it would take you 100 years to get there. But instead, it only takes 10. Of course, this probe is screaming past. There's no way to slow it down. It's going to be a flyby when it goes past Pluto. But otherwise, we wouldn't be able to get there at all in under 30 years or something like that. So this is a great trick, and that's how it works. Okay, there you go. And I'll write down the time now, 11:45, which means I probably took too long, slingshot, to answer that as well. But there you go. That's how that works. I love that kind of stuff. So much fun. And it is funny the way orbital mechanics works. That if the Earth is orbiting the sun at 30 kilometers a second, about 18 miles per second, and if you shoot a probe toward the sun from the Earth to the sun as it's going around, that probe is going to go on its own orbit, but it's got a velocity this way that you've given it from the rocket, but it's still moving. It's trying to move 30 kilometers a second that way. So it goes on this crazy elliptical orbit. You have to basically shoot it. If you want it to fall straight into the sun, you'd have to shoot it away from the Earth at exactly the same speed that the Earth is moving this way. It's kind of like if you're driving down the road and you throw a ball out the window, right? Somebody catching it, that ball's going to be moving at the same speed the car was. If you want that ball to stop dead on the road, you have to throw it behind you at the same speed the car is moving forward. Same sort of thing with orbital mechanics. So if you want to drop it into the sun, you have to shoot it this way at 30 kilometers a second, which is hugely fast and really hard to do. So you don't do that. You send it this way as fast as you can. It goes on its own orbit. If you plot that orbit just right, it'll come back to the Earth, and you can use a slingshot to actually remove energy from the probe and drop it toward the sun. And then as it drops toward the sun, it actually winds up going faster. It has less energy, but it's going faster. It's crazy. But that's the way it works. It's a little non-intuitive, and you have to be super careful about it when you're doing that kind of stuff when you're thinking about it. Okay. People are asking me technical questions that I cannot answer. Roman Sill is asking me about fields of view in an eyepiece. You'd have to look that stuff up online. If you want to know what kind of, you have a telescope or the field of view, it depends on all kinds of stuff. A lot of times, and I'll say this carefully, I get asked a lot of questions on Twitter and a lot of questions on email and sometimes in these chats where you could simply go to Google and look it up. There are a billion web pages out there where stuff gets explained. Sometimes these answers are, the questions you're asking have answers that are sort of independent of who answers them. I could answer them, somebody else can answer, it doesn't matter. Other times, they depend on the explanation itself. So I can, if you're asking me about gravitational slingshots, sure, anybody can answer that, but they're going to answer it a different way than I might. If you're asking, how do I calculate this, go online. It's math. It doesn't matter who explains it to you, right? Well, I mean, it does, but it's a series of steps that you can do. But if you're asking something a little more general, and then it depends on who's talking about it. I might be able to explain it better than somebody else, and somebody else will be able to explain it better than I can. And then it's dependent on who's doing it. That's perfectly understandable. But I would have to say, on Twitter and by email, 90% of the questions I get are just Googleable. It's like, I need to know, how massive is Jupiter? Oh, let me Google that for you. So, if you have questions like that, I would just say, just Google them. I don't have any problems with you asking those kind of questions or wondering about them or anything like that. It's just easier. And then all I would do is I would Google it and then I would answer it. So remove the middleman, in this case me. All right, so scrolling down. Johnny Bo Anderson is asking why this chat doesn't auto-update. If you, actually, and somebody answered right after, right after that, saying, play the video from your main Google Plus feed, and it'll auto-update. And sometimes if there are too many people watching a Hangout on air, it won't auto-update either. And Google Plus knows about this. They're actually the ones who talk to me. I talked to them about it. They talked to me and told me if there are too many people, it could be a problem. Wow, that's an interesting question. Darren McKinnon asks, in a binary star system, could interaction between one star's emissions and the other star's magnetic field produce some form of aurora, even though it would be interacting with hydrogen rather than other elements? That's interesting. Yes and no. The reason we can see an aurora at all on the Earth is that basically the sun's solar wind, that's made of charged subatomic particles, blow out from the sun, are captured by the Earth's magnetic field and then funneled down to the Earth's north and south poles, where they slam into our atmosphere and cause our atmosphere to glow like a neon sign, literally like a neon sign. The only reason we can see it is because it's dark at night and the aurora is very faint, and so you can see it glowing. The aurora happens during the day, you just can't see it because the sky is bright. It's there, it's glowing, but you can't see it. With a star, yes, in fact, now that you say it, and I'm thinking about it, if you go to the Solar Dynamics Observatory website, SDO, just look it up on Google and take you there, or you go to helioviewer.org, helioviewer.org, you can look at solar satellite observations of the sun at different wavelengths. Now, the sun has a magnetic field, and so this thing, it's not like the Earth, which just has a north and a south pole, like a bar magnet. So, you can kind of picture those sort of donut-shaped magnetic field lines you see in all the diagrams of a bar magnet. The sun has hundreds of these things, and they pop out of the sun's surface, and they go up and then back down near the point where they erupt out. So instead of having a gigantic single bar magnet, it's like having lots of gazillions of little bar magnets all over the sun. So the magnetic field north pole and south pole are right next to each other. You get those looping magnetic field lines like this. You can see those if you look at the sun in X-rays and ultraviolet, because they're hugely magnetic, and the plasma, the gas that's been ionized or at least excited by the sun's energy can be seen following those magnetic loops. In a sense, that's an aurora. And you can even kind of say, well, this gas comes up, goes back down, and slams into the surface of the sun. These are called coronal loops, by the way. When the gas goes up and follows that loop and comes back to the sun, it slams into the sun's surface. There's a hot spot there, right where it's hitting the sun. There's a hot spot. It's being heated up by this stuff slamming into it, or at least, I don't want to say heated up. It's given energy. That's probably a more physically accurate way of describing it. And then it glows. Well, that's what an aurora is, right? You're taking subatomic particles, slamming them into a gas, and then it's glowing. So in a sense, all of those little hot spots are an aurora. And so if you have two binaries, two stars, a binary star, and we see these all the time, they're very common in space, two stars going around each other. If they have strong magnetic fields, yeah, you could have funneling of one star's gas onto another one that'll slam into the surface and have little hot spots, and you get an aurora. Perhaps if you had a satellite orbiting these stars, observing them in these wavelengths, in the ultraviolet and X-rays, you'd see that. An aurora like the Earth, it's different than the aurora like the Earth, but that's funny. I'd never thought of that before. I could be totally wrong here, by the way, but that seems that strikes me as being accurate. So there you go. Wow, we're getting a lot of questions here. Don't forget to +1 this, by the way. If you're a member, if you're on Google Plus, if you're just logged in here off Twitter or whatever, you're not a member of Google Plus, don't worry about it. But if you are, go ahead and +1 this, and that helps me know how many people are in here. It's actually it's really hard to know. That's something I should talk to the Google Plus folks about and see if they can have a way of saying how many people were in the room. Thomas Kirkpatrick asks, should space exploration be privatized? That's one of those questions. It's a little bit loaded in that it's a very general question which covers way too much ground. Should it all be privatized? No. Should some of it be privatized? Absolutely. So you see what I mean? That there's two ways to answer it. I've answered this many times. As a matter of fact, oh, drat. I may have a Q&BA from last week, which I haven't put up yet, which answers this. But very briefly, it is not in a private company's best interest to build a lunar base, despite what Newt Gingrich might think. Why would they spend $100 billion or more to do this? What's in it for them? How are they going to make money off this? They can't. There's no way. This is only something a government can do, a government which has huge pots of money. And government can do what's best for the population as opposed to what's best to make money. Governments have different goals than corporations do, or at least they should. I'll put that out there. It's not necessarily true, but governments can take $1 billion and fund that into purely scientific exploration. And they should do this. As a matter of fact, I think they should be mandated to do this. They should always have money for this. But companies can't do this because they can't turn a profit. They'll go out of business if they do that. Because the ultimate goal is different. You know, how do you tell your investors, yeah, we just blew $10 billion to build a lunar base, and we're never going to get that money back? Well, you're done. But governments can do this. So governments have historically done this. Lewis and Clark, Magellan, De Soto, Columbus, you know, all of these guys, all of these white guys, because they were all from Europe, if I can do my Eurocentric little speech here, these were funded by governments. After that, the private companies come in. So that's what should happen. NASA, for example, as a government agency, could build a lunar base if their budget were tripled. But private companies wouldn't be able to do that. But then later on, you know, private companies like SpaceX, or there's a whole bunch of them out there, Blue Origins, Armadillo, you know, all these guys, they could then follow and send supplies to the lunar base, or bring astronauts back and forth, or whatever, or launch communication satellites that communicate with the base, or whatever. That's how you do things. And that it's sometimes the way we've done things traditionally is a bad way, but a lot of the times the reason we do things the way we've been doing them for hundreds of years is because that's what works. In this case, it's the latter. That's what works, and that's why we do it. I love privatized space. I think it's a great idea, but I think we need governments to plow the road, to pave that way to do that. Let's see. Oh, okay. See, I'd answer this one question, but I have no idea how to pronounce this guy's name. I'm so American. This looks like a possibly a Dutch name. Stefan van Oudenarden? Oudenarden? Is that right? See, Slavic names I do. I've got Slavic ancestry. So if you don't have any vowels in your name, I can get it right first try. If you have too many vowels in your name, I'm all over the place with it. So Stefan van Oudenarden asks, if you have a planet in the habitable zone of a binary or more system, and the stars are both in the center of the system, so you've got two stars with a planet, let's see here, two stars, I guess, with a planet orbiting them both here. I'll do it like this, right, like that. How would that look from the planet's surface as an observer? Well, pretty much like you'd think, right? You'd see two stars in the sky, two suns in the sky, not just one like we do. I've actually thought about this in the past because it's interesting. Would it look like Tatooine, for example, when Luke is there on the desert plain with his hair flowing? I'll steal this from Will Wheaton because he does this at Woodstock. And he's watching the sunset. I'm not sure. The thing is, if you had two stars like the sun, for example, well, you know, the habitable zone for the sun, the Earth is basically right in the middle of it. It gets very complicated depending on if the planet has an atmosphere and how dark or how light it is and all that kind of stuff. But for the sake of argument, let's say the Earth is in the middle of the sun's habitable zone. In other words, if you were any closer than this distance to the sun, it'd be too hot. If you're any farther than this distance, it's too cold, and the Earth is right in the middle of that. So any planet in that region would have liquid water on its surface, and we'd call that in the habitable zone. It's a lot of simplifications. However, if you have two stars and they're both like the sun, that habitable zone moves way out, right? It actually gets thinner too because of the way the physics works. So because it's farther out, the stars will look smaller, right? It might be twice as far from the sun. I'd actually have to do the math. I don't think it wouldn't be twice as far. but it would be significantly farther out, and the stars would look smaller. So at sunset, instead of the sun looking yay big, it would look smaller. It gets more complicated because the planet has to be far enough out that the gravity of the two stars, right? If gravity of one star, you can have orbits really close in, really far out. They're all stable. When you have two stars, if you have an orbit that's too close, then when the two stars are configured like this, you're feeling more gravity from this star, and when they're like this, you're feeling less and less. So you're feeling different gravity along your orbit, and that makes the orbits all screwed up, and you could eject the planet from the system. So you have to be far enough out that physically the two stars sort of are far enough away that their gravity kind of looks like the gravity from one star. I like to tell people, think of it as like headlights on a highway. When they're up close to you, you see two headlights. When they're really far away, it looks like one headlight. And it's the same sort of thing. When you're up close to two gravitational sources, they act like two gravitational sources. From far away, it looks more like one. So there's that. And you have to account for the gravity of the two different stars and how hot they are. So if you have two very cool stars that are orbiting very close, then it gets a little bit easier because their masses are lower. The habitable zone is wider, I believe. I'd have to do the math, but I think that's correct. And the habitable zone is relatively stable when you're orbiting two stars. In fact, there was a star, GC667, which was just announced to have, it's a triple star. It's two stars orbiting each other close by, and a third star farther out orbiting the two of them. So these two guys are doing this, and then this guy is doing this, and around this third star is a planet, and it's close enough to this star that the gravity of these two stars doesn't really disturb the orbit. The orbits are stable. And it turns out that the two stars are fainter than the sun and cooler. The third star is even cooler than they are. And so this planet actually is in the habitable zone of that very cool star and actually has a stable orbit, which is interesting. It's a super-Earth that's got like 4.5 times the mass of the Earth, GC667c. You gotta love that. The two stars are GJ667a, GJ667b, and then GJ667c. These are capital letters. And then a planet orbiting this is GJ667c little c, because there's already a b and it's a mess. What a horrible nomenclature. But it's the best we can do. And so, that would be amazing. You'd have this one star in the sky. It'd be huge, too, even though it's a tiny star. The planet's orbiting very close. And when that sets, there'd be these two other stars, or probably even during the day, you'd be able to see them. These two other stars that are sort of more orange than the sun is, you'd see them really close together, too. It'd be fantastic. All these science fiction scenarios that you see, where you have a double star setting or a triple star or whatever, they're maybe possible. We're finding planets in these crazy systems where you can actually see this stuff. To me, that's one of the most fantastic things we're doing right now. Is finding these planets is amazing. It's incredibly difficult work. If it were easy, they would have been discovered decades ago. But the fact of the matter is that the first planets orbiting another star weren't found until early 1990s. The first planets orbiting a sun-like star, one literally like the sun, that wasn't found until 1995. And it's only been 17 years. Gosh, it's been that long. It's only been 17 years, and we've found hundreds now, potentially thousands. And we think that there are billions out there orbiting stars. And because planets are so common and stars are so common, you can start to say, statistically, there are going to be these really weird systems. There may not be many of them, but they're probably out there. And sure enough, GJ667 is a weird system. It's two stars, the third one orbiting the two with a planet around this one here. And it's like, but the amazing thing about that is that it seems like a really weird system, but it's really close by. It's only 20 light years away, if I'm remembering my numbers correctly. When you find something that close by, 20 light years away, if I take a model of the Milky Way galaxy, this is 100,000 light years across, right? And the sun is halfway from the center of the galaxy to the edge, like right about here. All the stars you can see in the sky, I could cover up with the tip of this eraser, this pencil, right? That's thousands of light years. 20 light years is nothing compared to the size of the galaxy. When you find a really weird system that's really close by out of a huge set of these systems, it makes you wonder. There might be a lot of these things out there. It seems like a huge coincidence that something that weird would be that close. So to me, all of these signs indicate that planets are everywhere. And it almost doesn't matter how weird of a system we find. There may be planets around some of these things. I used to always make the case, to science fiction people at least, are we living in in Asimov's Foundation universe, or are we living in a Star Trek universe? In other words, are there habitable planets everywhere, like in Star Trek with aliens on them, or is it more like Foundation, where well, actually, now that I think about it, that may be a bad analogy. But in Foundation, there are no aliens. There are planets everywhere, but no aliens, just humans colonizing the galaxy. Everywhere we go, all the planets have primitive life on them, and we colonized them and terraformed them, made them like Earth. And it's interesting. It's starting to look more like a Star Trek universe, that there are these planets everywhere that could have life on them. I'm starting to think I don't like this analogy anymore, because it's not habitable versus uninhabitable planets. It's intelligent aliens versus just us. But the point I'm making here is that it's looking like there are planets everywhere. Most of them will not be Earth-like. Most of them will not be in orbits that have liquid water on the surface. They may be too hot or too cold for that. And I'm ignoring chemistry like ammonia-based, methane-based, whatever chemistry. But it looks, we're starting to get to the point where we can find planets that are lower mass than the Earth, and we are finding those planets. They're very close to their stars and very difficult to detect. Or there are other ways we're detecting them as well. But the point is they're not in the habitable zones of their stars that we've found yet. But we're getting there. We find planets in the habitable zone that are too big, that are bigger than Earth, and we're finding smaller planets than the Earth that are not in the habitable zone. It seems like there's just a matter of time before those two things connect. And we find something that looks like the Earth or Mars or Venus or whatever in the habitable zone of a star. We're that close. And it's not just going to be stars like the Sun. They're going to be tiny, cool red dwarfs. They're going to be massive blue stars, double, triple systems, whatever. The galaxy is buzzing with planets. And I think that, to me, is probably the most significant scientific discovery since the discovery of dark energy in 1998. It's fantastic. I love that. It's just one of my favorite things in the whole world, or whole worlds. It is now 12:06 my local time, which means we're out of time. So, just see if there's anything that's a problem here. No. Okay, so let me wrap it up then. Thank you, everybody, for coming this week. It's been terrific, as always. I love getting all these questions from you guys. There may come a day when I answer more than 4 questions in less than an hour. That's probably never going to happen. I wouldn't count on it. So, just to wrap this up, my name's Phil Plait. I tweet at Bad Astronomer on Twitter. You can find me here on Google+. I post several times a day. I have a daily thing I call the BA Fact, where I post just a fact about astronomy or space or whatever. You can go to that. I got the Q&BAs, which I do every Sunday. I may mix that up a little bit because I'm going to be traveling. Next week, for example, I'm going to be in Philadelphia, in Bethlehem, Pennsylvania, I should say. I'm flying to Philly, but going to Bethlehem, Pennsylvania to participate in George Schraub's Concert 21812, because it's February 18th, 2012, where I'll be performing his song Death from the Skies with him on stage. So I will be on a plane, I think, at the time I should be coming back here to do Q&BA. So I don't think there'll be a Q&BA on Sunday next week. But you should go to George Schraub's website, HRAB, and if you're in that area, go to the concert. It's going to be awesome. This week, by the way, I'll be at Eastern Michigan University at Ypsilanti, Michigan, on the 15th, Wednesday, giving a talk, Death from the Skies. You can look that up on my blog. I blog for Discover Magazine. Go to badastronomy.com. It'll take you there. And finally, Science Getaways is a vacation where you can do added bonus science. It's a regular vacation you can take where I'll be there and I'll have other scientists there. We're going to do nature hikes at a dude ranch in Colorado. And there's going to be basically bonus science. We call it Vacation with Your Brain. And it's for science dorks like me. And it's going to be at this fantastic dude ranch called C Lazy U. The letter C, lazy, U, because you're seeing yourself being lazy, because they take care of everything for you. You can do whatever you want or not do whatever you want. But we'll have science talks about geology and biology, then going out for hikes. There's horseback riding, archery, fishing, swimming. There's a spa there. We'll be doing stargazing at night. The food is fantastic. I went there and we We had lunch there, and it was so good. You can go to sciencegetaways.com, or you can go to the right-hand side of my blog, and you'll see a little picture there of a brain with airplane wings. That's our logo. You can click that, and you can find out all about that. So I hope to see some of you there. And that is it. Thank you very much for listening to me blather on, as I tend to do on these things. Have a great weekend. Thanks, everybody, and bye-bye. And now here's the awkward moment where I have to find my Hangout window and actually exit. This happens every week. You'd think I'd learn. All right. Bye, everybody. Thank you.